Okay, I'm going to put the lecture content part on hold for a second before we move on with dealing with variability in populations. It still says variance up here. I want to give you what I think is some really good study advice. In this course, anytime I give you a new symbol, there's three things to know about it. If you study with flashcards, for example, or some equivalent thereof, every symbol should have 3 flashcards, because there's 3 things to know about every symbol I give you. The first thing to know about this symbol is, what's it called? It's called population variance. How is it defined? Population variance is the average squared distance of raw scores from the mean. That's the second bit of information. And of course, the third thing is, what's the formula? Now, because we're doing this class online, you don't have to have the formulas memorized. You can have them right there in front of you. But when I teach this class live, formulas have to be memorized. So it's one of those things that you want to be at least familiar with what the formula looks like if you're not going to memorize it, so that you don't waste quiz time or exam time trying to hunt down the correct formula. So for every symbol I give you, there's 3 things you really just should have immediately come to mind. What's it called? How do I define it? And what's the formula to calculate it? So this doesn't really have anything to do directly with the lecture content, but I find that's helpful for a lot of students in trying to prepare for quizzes and exams, that they think in those terms. Okay, so now we can continue on with what comes next. So the next thing for us, we've computed the variance for population variability. Now, the third and final measure of variability is called standard deviation. This is the concept for where we're trying to get to. I called it the promised land in an earlier video clip. This is the destination. Let's define it. Standard deviation is the average distance between raw scores and the mean. So variance is the average squared distance between raw scores and the mean. Standard deviation is simply the average distance between raw scores and the mean, which is what we're trying to do this whole time. So in order to do that, you have to do variance first. Variance is a step along the way. Well, what symbol are we going to use for population standard deviation? That same lowercase Greek s, but without the exponent on it. Because the scores we're dealing with now, the values you're dealing with, are not squared. It's simply the average distance. Well, if you've squared something, how do you unsquare it? You take the square root. So I could write this a couple of different ways. So population standard deviation is the square root of population variance. Or I could write it with the formula in there instead of the symbol in there. Same thing as to say that it's the square root of the sums of squared deviation scores over the number of scores. Right? That's the symbol for variance, and that's the formula for variance. Same diff, whichever way I write it there. So all this says is, to get standard deviation, all I have to do is get the square root of variance. So for the data we've been working on, 54321, we said that our variance was 2 points. So standard deviation is the square root of 2. And when you grab your calculator and you compute the square root of 2, you should get a long infinite decimal. So remember our class rules, always, always, always. Round to 2 places. So when we look at this rounded to 2 places, we're going to get 1.41. So think about that data. I erased it, but think about that data. 5, 4, 3, 2, 1 were our scores. And the question is, on average, how far are those scores away from the mean, which was 3? Well, on average, they're just under 1.5 points away. That makes sense to us. There's sort of an intuitive logic. Variance is not something that you can look at, most of us, and intuitively get a sense of, because the distances are squared, and so it's kind of hard for us to wrap our heads around it. But this makes sense to us. This is used in descriptive statistics. So variance tends to be used for inferential. Standard deviation is what we tend to use for descriptive. And we'll get further into that later on in this chapter, how we can use this to amp up our descriptions of our data. So with that in place, we have covered all three measures of variability. We did range, which works the same for samples or populations. Then we did variance for populations for the second tool. And now we've just done, pretty easy from variance, standard deviation from populations. So now we need to go back and consider, what if our data instead comes from a sample? The key here is that we're trying to measure variability, of course. And when we're doing that for a whole population, we have all the data. It's all filled in there, hypothetically. But we know a sample isn't all the data. It's just a sampling of the data. If the population is 100 scores, my sample might be 5. Well, let's think about that for a second. I'm going to put a bell curve up here, a normal curve. So this is my population of scores. That's all the scores. They're all present and accounted for. And let's just think about range. It's easiest to think about this in terms of range. Well, we go to the lowest score, we go to the highest score, and we subtract, and we know the range for this population of scores. Great. But now we're going to pull a sample. We'll go with 5 scores again. I'm going to pull a sample of 5 scores out of this population. Well, where are most of the scores located? Most of the scores are up here in what we would call the body. The central lump, if you will, is the body, and then the little tails sticking out are called tails. So for this kind of curve, we've got a body with 2 tails here. Well, if this is where most of the scores are located, this is where most of my sample is going to come from, right? If I've got a jar filled with marbles, and it's got 99 white marbles and 1 red marble and 1 blue marble, when you reach in there, you're probably going to get one of the 99 white marbles, right? It's a very low probability that you'd randomly get either the red or the blue marble. When I reach into my population and I randomly pull people out of it for a sample, most of them are going to end up being in this area somewhere. Maybe not all of them. I might get one from over here. I might get one from even all the way up here. Now let's think about that. What would the range of the scores for the sample be? Much less than the range for the population they came from. So let me say that again. The variability of scores in the sample is almost always less than the variability of scores for the population they came from. The population has all the diversity represented. All of it. But the sample doesn't have all the diversity in it. It just isn't likely to. It could. You could do a sample where you just happen to get the lowest scoring person and you just happen to get the highest scoring person, but that's pretty rare. So that's why we say almost always. So the variability of scores for the sample is going to be less than the variability of scores for the population they came from. That's kind of problematic for us. The goal of the sample is to represent the population, not replace them. A sample is a tool, not an end. So in other words, it's not really our goal in research to understand the sample. It's our goal in research to use the sample to understand the population they come from. So when I say I want to know about the variability of this sample, what I'm really saying is I want to know if the variability of the sample as it represents the population. So what this means is if we know that again, thinking about range, that our range value is going to be too small. It's going to be too low. It doesn't have the full range in it. If we know that's reliably true, we can adjust the calculation so that when we calculate the range for the sample, it expands a bit to better represent the population it comes from. Well, we're not doing that with range, but we are doing that with variance and therefore standard deviation. We have to make this little correction, if you will, this little adjustment, so that what our measure of variability for the sample is a better estimate of the population. That's really what we're looking for here. So as a result, the math has to be just a little bit different. So we'll see how those formulas change in the next clip.